I want to quickly step through the solution here to number 9. The actual using the map to find the minimal sum of products form should be pretty similar to the other exercises, but here we're starting with a truth function. And so the goal here is to turn this truth function into a Carnot map, and then use that Carnot map to find this minimal sum of products form. So when we look at the truth function, this, just like it was before, we can derive an expression from this. Any place where this function is 1 is going to be a term that we need to include in our Boolean expression. So we're going to start with the canonical sum of products form, which would be what we just did in the last section, creating the expression that represents this function by only considering what we need to make the output of that function 1. And so we have a term for each of these 3 rows that makes the function 1. So now that we have this expression, now this becomes just like the first 2 exercises. Or rather, I guess, once we create our map, now we have we have a starting point to create our map, and then we get to the point where we're just doing the same thing and interpreting that Carnot map. So that's the next thing we'll do here, is make a Carnot map that represents this expression. So the way we're doing that is we only have 3 variables, so the standard map here is this sort of 4x2 matrix with the x1 and x2, different combinations of those variables on top, and then x3 along the side. And if we look at each term of our canonical sum of products form, we have x1, x2, x3, which is going to be this one in the top corner, because this is the square that represents x1, x2, and x3. We look at sort of the intersection of those to find where that 1 is supposed to go. The second term, x1, x2, and not x3, x1, x2 is still in this first column, and not x3 is in the second row, so we get the 1 down here in the second row. And then finally, not x1, x2, and x3, not x1 and x2 is right here, and then x3 would come from the top row, so that's where we get the 1 there. So we translate our sum of products form into the 1s in our Carnot map, and if you look at it, the truth function over here and the Carnot map here really deliver the exact same information, just in a different form. This is laid out sort of in order of the inputs, and this is just organized in a different way to let us do this game of trying to figure out what the minimal combination would be. But it's the exact same number of 1s and the exact same combination of variables, just written in a different format. Okay, so then finally we need to group these 1s in our Carnot map. So one option to do that, we might think we can group these. That would be fine. And then we have this other one kind of sitting out by itself, so that seems like maybe it could take its own group. So we have these 2 groups, which is a pretty small number of groups. But we want to remember that if we can make a group larger, we want to do that. We want each of our groups to be as large as they can possibly be. And we can make this group larger because, again, we can always wrap around the edges of this map to the other side. So we can actually extend this group so that it ends up capturing the 1 on the other side. And that would look something like this. Whoops. There we go. So now we have a group for these 2 1s that are adjacent to each other. That's a pretty obvious group to make. And then the other group is going to not just include this single square, but it's going to wrap around to include this other square. And again, even though this seems kind of redundant, we always want to overlap these things, or we want to allow ourselves to overlap these things if it gives us the ability to make a group larger, because a group of 2 elements has the potential to eliminate one of the variables, whereas a group of just 1 element does not give us the possibility to eliminate one of those variables. So then finally, with these 2 groups, we translate this into our minimal sum of products form, which is going to be, let's start here with the vertical group on the left here. x1 and x2 are both sort of required for this column, but x3 changes from x3 to x3 not, so that variable should be eliminated. So the only thing we have in our first term is the x1, x2. And then in the second group that wraps around, both of those elements are in the x3 row, so we're going to need x3, so that's where that comes from. But if we look at what these two squares are coming from on the top, we have x2 to x2, that doesn't change, but we have not x1 to x1, which does change. So x1 could be eliminated here, and it just gives us the term x2 and x3.